going to do is we're going to talk about limiting reactants. And let's think about cookies because it is Girl Scout cookie season. So that's all I think about is cookies. And if we wanted to make some cookies and all we had was this much sugar right here, that would be hard to make very many cookies. In fact, this would limit how many cookies we'd be able to make because we would run out of our sugar at some point pretty quickly. So that's what we're going to look at with chemical reactions, is that there are limiting reactants involved. It's the stuff that you run out of first, and then it's going to dictate how much of your product you can produce. So what we have seen up until this point, actually let me kind of rewrite this. Up until this point, we said, okay, if you start with a certain amount of one thing, you've got this mass of A, and we know that we've got a mass of AB that's produced. If you see something like that, chances are that's going to be a percent yield problem, and it might ask you to solve for percent yield, or it might ask you to calculate an actual maybe. So that's what you would see there. In this case, what we're going to be looking at now is limiting reactant problems. And in this case, you are given masses or volumes or molarities, you're given amounts of both of your reactants, and then you're asked to determine how much of your product you can form. So instead of just dealing with stoichiometric amounts, in other words, amounts that are all used up, exact proportions of things, we're going to be mixing two reagents, which means we have non-stoichiometric amounts. And what we just need to do is figure out which one of these reactants we're going to run out of first. Okay, yummy sandwich that we have here. Let's say our sandwich recipe is equal to 2 slices of bread, 1 piece of ham, 3 pickles, and 5 yummy sardines, and that equals 1 sandwich. So if this is definitely the exact amount that's needed, and you open your fridge and you see 8 slices of bread, 10 pieces of ham, 9 pickles, 20 sardines, and we just went ahead and put that underneath, just like we do in our balanced reactions. So if we wanted to figure out how many sandwiches we could make, what are we going to be limited by? What are we going to run out of first? Pickles. How did you do that? How many sandwiches are going to be made? 3. So what you did, here's pickles right here, you took your number that you're given, your 9, and what'd you do with that? Divide it by 3. So you took your amount in moles and you divided it by your coefficient. So you did that to determine that ratio of what is needed and what you've got available. So we could easily do the same thing with our bread. You divide it by 2, so how many sandwiches based on your bread could you get? 4. Well, make a lot of sandwiches based on your ham. This was just 3 for our pickles, and then 4 for our sardines as well. So limiting reactant is what the small one is, so that was our pickles, meaning we're only going to be able to make 3 sandwiches. Even though we've got a whole bunch of ham, we can only make 3 sandwiches. And then if we wanted to determine how much of which reactants are left over, let's go look at our bread. If you made 3 sandwiches, how much bread would you have left over? 2 slices. We could do that for each of these and figure that out. So that's what we're going to do with actual chemical reactions. Here's an example where we have 2 moles of hydrogen plus 1 mole of oxygen gives us 2 moles of water. So if instead of that we actually start with 10 moles of hydrogen and 7 moles of oxygen, considering what we did with those coefficients, what are we going to run out of first? Hydrogen, good. So we divide this by 2 and you get 5, whereas you divide your oxygen by 1. So what I'm looking at is my balanced equation, and we get 7 here. So we see that we would run out of our hydrogen first. So in this case, the limiting reactant, it's the reactant that you run out of first, and it happens to be hydrogen in this case. The excess would be oxygen. Don't worry too much about this terminology. These mean exactly the same thing, reactant or reagent. It's just the stuff that you start with, stuff that you're putting together. So we have some steps that we can use to follow this, and there's no great place on your handout to be able to write this. What I would do in the bottom right-hand corner I think I'd make a little a list of 4 things. They're pretty short. So, first thing, whenever we're doing stoichiometry, what should we always start with? There we go. Balanced equation. And as part of that, I kind of like to say that you're going to write info underneath, because that sure helps to ensure some success. Okay, so once you've got your balanced equation, and remember you've got amounts of both of your reactants, what do you think you're going to convert those amounts to? Moles. So convert givens to moles. So when we just did those examples with the sandwich and stuff, what did we do with that number? To be able to figure out which one we ran out of first, divide by coefficients. Divide each by coefficients. And then finally, what we're going to do is we're going to find out which one's smaller, and we're going to use smaller as the limiting reactant in our stoichiometric problem. So that is our list of steps that we're going to follow. It's not the only possible list of steps. There's another way to do this, and I'll probably show you that halfway through. So first example that we've got, we start off with some aluminum, add it to sulfur, and we get aluminum sulfide. Then we balance. We write information down underneath that says that we're starting with 20 grams of aluminum and 20 grams of sulfur. And the question is, how much of this aluminum sulfide in grams will be produced? And then we've got another question in there as well. So, step 1 has been completed. Step number 2, take each of those givens and convert them to moles. So, 20 grams of aluminum and 20 grams of sulfur. We know 1 mole of aluminum has a mass of 26.98 grams. 1 mole of sulfur has a mass of 32.06 grams. I'm sure that you guys have calculators in front of you. Clicking away. And I'm going to go ahead and just write down some numbers, but please solve through these as we do it. So when we do this first one for aluminum, we get 0.741 moles of aluminum. And for the sulfur, we get 0.624 moles of sulfur. We have just done step 2. Step 3, what should I divide this by? Okay, so 2 and 3. So step 3 tells us to divide by the coefficients. So we get 0.371 for our aluminum and 0.208 for our sulfur. Which one of those guys is your limiting reactant? The sulfur, because this one is the smaller one. That is the limiting reactant. This is in excess. Maybe I'll even make myself a note of that up here, that this is the limiting reactant, our sulfur is, and aluminum is in excess. So now that we've got that information, our last step says that we take what we just got and we use that in our stoichiometric equation. I could start with my 20 grams of sulfur, but I hate doing extra work if I don't have to. So instead of starting with grams of sulfur, what might be easier? Moles of sulfur. So let's go ahead and start with that 0.624 moles of sulfur that we have right there. Saves us repeating that step. So we can get rid of our moles of sulfur. Hey, where are we trying to go? What am I trying to find from this? The aluminum sulfide, good. So we know that this is our limiting reactant, so we want to find out information about our aluminum sulfide. So we're getting rid of our moles of sulfur and going to moles of aluminum sulfide. 1 mole of this to 3 moles of this. Now we've got it as moles of aluminum sulfide, which we can get rid of. And go to, let's see our number here. It's going to be 150.14. 150.14 grams of aluminum sulfide. We throw that into the calculator, and we get 31.2 grams of aluminum sulfide. We have just answered that first question. First question is, how many grams of aluminum sulfide will be produced? Okay, looks like everybody's caught up. So now the second part says, well, how much of which reactant will be left over? So I want to figure out which reactant's left over. The aluminum. So the aluminum is in excess. I want to figure out ultimately how much of my aluminum is left over. Do you know what to do? Okay, what would you do?
Subtract the sulfur from the other group. So subtract 2.0837.
Okay, I'm going to subtract. You're right about that. But I'm going to say that I know I've got 31.2 grams of this that's produced. Conservation of mass, right? I know that I used all of this. So if I used all of my sulfur, my aluminum that I used plus my sulfur should add up to my 31.2. So for this, we're really going to say 31.2 minus what? Minus 40. Actually, that's a good way to do it. Or you might just think 20, in which case, I'm going to do it this way, but someone said 40, which would also kind of work in that way. But here we see that we have 11.2 grams of sulfur. What? What is that grams of sulfur? That's how much was used. That's how much was used. That's the important part to see from this. So let me, did I say the wrong thing? Yeah, I wrote sulfur, sorry. See, you guys are following. Okay, so 11.2 grams of aluminum is used. So if we write that down, 11.2 grams. Let's just look at this really quickly, because this is a great way of showing conservation of mass. That the reason we could do this is we said 11.2 plus 20 grams, that's what we started with. We started with 31.2 grams, and we ended with 31.2 grams. So that's all we did was a little subtraction. But that's not what the question asked for. It doesn't ask for how much was used, it's how much will be left over. So what should we do now? Excellent, excellent. So we know we started with 20 grams of aluminum. But we only used 11.2 grams of aluminum. So that difference of 8.8 grams of aluminum is what is in excess. So that is the answer there. Now notice that this is a great way to do this when you've just got a situation where you've got these three different substances, and it makes it really easy to just do a subtraction. If it was a double replacement reaction, you wouldn't be able to do that. There's another way, and we'll do that for the next one. Okay, so it was just brought up again that we could actually just take our 40 grams and subtract our 31.2, and that would give us this value. Yes, you could have done that, and that's an easy way to do it. That works, yet again, that would work if you have those three variables. But again, on a double replacement, it wouldn't work because you just couldn't do a simple addition or subtraction in this case. So this next example, I'll show you another way of doing it. And I just wanted to make sure that you guys know how to do that subtraction from what was used and how much is left over, what is in excess. Okay, next one. Here we've got hydrogen plus oxygen gives us water. And we know that we're starting with 2 grams of hydrogen and 10 grams of water, and the question is how many grams, 10 grams of oxygen, and the question is how many grams of water are we going to produce? So there's what we know. We take each of those grams and we're going to take them and convert to moles. So I'm going to say 1 mole of hydrogen has a mass of 2.02 grams. 1 mole of oxygen. What's the mass of 1 mole of oxygen? Awesome. So I heard 32 all day long. I've been getting 16 from people. So 32 grams of our oxygen. Don't remember that it's diatomic and then forget what to do about that. So you have to make sure you double that mass. So we get it to this point. We can do some calculations and we get 0.99 moles for our hydrogen and 0.313 moles for oxygen. You have just done step 2. Now what? Hydrogen should be divided by 2 and oxygen by 1. So this gives us 0.495 and this one is still 0.313. So the answer, our limiting reactant, is which one? Oxygen. Limiting reactant, this one's in excess. So when we go through and do the problem, we are going to start with our limiting reactant, which is our oxygen. I don't really feel like doing all this work again, so I'm going to start over here at my moles of oxygen. So 0.313 moles of O2. And remember what we're trying to do now is we're trying to go to grams of water. So we get rid of our moles of O2 and go to moles of H2O. And 1 mole of oxygen, 2 moles of water. And for every 1 mole of water, there are 18.02 grams. And we add that up, as in we multiply it, we calculate it, and we get 11.3 grams of water. I based that on the fact that I had 3 sig figs, which is what I had right here. So I have 11.3 grams of water. We have just answered that first question. I want to do the second part in a longer way because if we had another part, again, if we had a double replacement, let's say there was something there, we wouldn't be able to just do a subtraction. So what we need to do is we need to think about the fact that oxygen's our limiting reagent, meaning we used all of this. So why can't we say, hey, if you use 10 grams of oxygen, how many grams of hydrogen do you use? So that's what we're going to think about now. Starting with the fact that we use 10 grams, or in other words, we use 0.313 moles of oxygen. That's the same as those 10 grams. Now what we want to do is we want to figure out how many grams of hydrogen is used when all of those 10 grams of oxygen are used. So we get rid of our moles of oxygen, go to moles of hydrogen. 2 goes with the hydrogen, 1 goes with the oxygen. Last step is to get it to grams. 1 mole is 2.02 grams for our hydrogen. Oops. And in this case, we see that for hydrogen, it's 1.26 grams. What does that mean? Grams of hydrogen that is what? Which one? It's used. It's that much that is used. I started with this much oxygen, and that means that I'm going to need, I need that much of my hydrogen in order to produce it. I see a question, a hand raised, and I think I know where this is going, but I will let you ask your question. What's your question?
Where's the other point
Okay. So, where's the other 0.04 grams? And what that question is based on, I got this earlier today also, is the fact that if we were to just, let me think about what color I want to use. Let's go back up here, up top. We produced 11.3 grams of water, and we know that we used all 10 grams of our oxygen. And here it says that we just calculated that we used 1.26 grams of our hydrogen. So where did the rest of that hydrogen go? The only reason it's like this is because of significant figures. It's kind of a faulty problem. You wouldn't typically get a problem like this where you have one that has 2 sig figs and one that has 3 sig figs. And that's the only issue here. And I don't like this problem because it makes it look like there was a loss of mass, and there's not. We just based it on sig figs. So let's ignore that for the moment and just pretend that it's not, we're not losing mass. We're still following conservation of mass. So now finishing with this, we know that this is how much hydrogen was used. The question is, how much of which reactant will be left over? Well, obviously it's going to be the hydrogen. We started with 2 grams of hydrogen, only used 1.26 grams. And really maybe what it comes down to is now that when we're subtracting this, we should really end up saying that you just go to 1 past the decimal, so 2.0 minus 1.26. Instead of saying 0.74, maybe we just say 0.7 grams of hydrogen is in excess, because our sig fig rules tell us that you just round to the least number of digits past your decimal when you subtract like that. So that's how we can clear that one up. So that is the second part of our problem. Okay, backside, or the other half of this. Here we have hydrochloric acid plus sodium hydroxide. And we get sodium chloride plus water. Everything's +1 or -1, so it is balanced. We can write our information underneath, and I can start by saying I've got 0.025 liters, there's another 0, of hydrochloric acid, and it's at 0.50 moles per liter. Over with my sodium hydroxide, I've got 0.0500 liters, and it is 0.15 moles per liter. So there's my information about my reactants. The question is, how much of my salt am I going to produce? So there is another way. Don't get ahead too quickly on this one if you're trying something, because I'm going to try a different way with you guys. I've just done step 1. Step 2 says to take my reactants and convert to moles. Well, I'm going to start that, but I'm not going to actually calculate it yet. So let's start. Let's start with our hydrochloric acid. We've got 0.0250 liters of our hydrochloric acid. And we've got 0.5 moles for every 1 liter. And for the sodium hydroxide, we've got 0.0500 liters of sodium hydroxide. And we've got 0.15 moles for every 1 liter. Now, instead of doing it like we have our set of rules that says, now go ahead and calculate the moles, then take that and divide by the coefficients, would it be possible to take each one of these and just take them all the way out? So in other words, sodium hydroxide, calculate your sodium chloride. Hydrochloric acid, calculate your sodium chloride. If we did it that way, which one would be the correct answer? Exactly, so the one that is smaller, that produces the least amount of product. So in this case, let's try it this way. This is another alternative for you. You're welcome to do it either way. I'm going to start with my hydrochloric acid. I've got it as moles of hydrochloric acid. Getting rid of moles of hydrochloric acid. Remember, this is the route I'm taking. I'm going to moles of sodium chloride. Pretty boring, 1-to-1 ratio because I look at those coefficients. Now we've got it as moles of sodium chloride. Get rid of moles of sodium chloride. Go to grams of sodium chloride. 1 mole is 58.44 grams. Can do the exact same thing now for our sodium hydroxide. We've already gotten rid of our liters and we have it as moles of sodium hydroxide. We can get rid of moles of sodium hydroxide and go to, just like we did with the acid, we're going to go to moles of sodium chloride. Again, looking at your coefficients. Now we've got it as moles sodium chloride. We just take it. 1 mole is equal to 58.44 grams of sodium chloride. And I'm going to pause while people calculate. All right, while you were gone, calculator buttons were flying. It was amazing in here. So we got these two values. We got 0.7 and 0.4-ish of our sodium chloride. Which one of those is the correct answer? 0.4. This one's going to be correct because this is too much. It's not possible. What we did was we looked at sodium hydroxide and we looked at our hydrochloric acid. According to how much hydrochloric acid we have, it says that we can produce a whole bunch of sodium chloride. But the truth is, we're going to run out of our sodium hydroxide before that can take place. So according to our sodium hydroxide, we can only produce 0.438 grams of sodium chloride. You always go with the smaller value if you choose to do it this way. So sodium hydroxide is our limiting reactant. Hydrochloric acid is going to be in excess. So that's what you should see from this. That might seem shorter than the other ways, but it really probably is not, because keep in mind that it was only to this point. Everything above that was what we did. The rest of that stuff below it was answering questions about how much of the excess reactant do you have. So in this case, we are done with the problem except for this last little part of the question. Is the resulting solution acidic or basic? What's left in the flask? Hydrochloric acid. There it is. You got some excess hydrochloric acid left over, so it is going to be acidic because that's what's in excess. It's still there. It did not react. Okay, so we have our last one here, and this is just taking ethane plus oxygen. It combusts and we get carbon dioxide and water. Balanced, it becomes that. We write information underneath. We've got 56 liters of ethane and 180 liters of oxygen. How many liters of that gas is going to be created? How do you guys want to do this? The first way or the second way? First way or second way? Second way it is. Okay, so we're going to do this the second way that we learned. So in this case, we're going to start with 56 liters of ethane. And we're going to start with 180 liters of oxygen. Oh, I'll pause and we'll come back and it'll be done. Okay, so now we have it all set up. And remember, don't be alarmed. When you're going from liters to liters, this naturally happens. Your 22.4s cancel out, makes the math really nice and easy. So everything cancels out. We do the math. What did you guys get for this first one?
12.
And the second one?
103.
They are so engaged. This is wonderful. And so that was liters of carbon dioxide. So which one of these is the limiting reactant? The second one, which would be what? Oxygen. is our limiting reactant. This guy, our ethane, is in excess. We can't really produce 112 liters, not possible. We can only make 103 liters. That is all.